Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's my pleasure to introduce Peter Toraba here. Peter got his master's degree from University of Slovakia University of Technology, and he had been with us how many years ago? 3 years ago, probably, as an intern.
2 and 4 years ago.
2.5 years ago, as an intern here in Microsoft Speech Product Group with Julian, right? With Julian, and today he's with Smart Desktop in Seattle now, a startup company, and today he's going to talk about one of his work when he was a graduate student. It's about Kneser Ney smoothing with a correcting transformation for small data sets. Okay, thank you.
Thanks. So I would like to thank you, A, for inviting me to give a talk. And so I will speak about my previous work on Kneser Ney smoothing algorithms. And so once I was told that there is no way I could improve Kneser Ney smoothing, and as I like to be challenged, and I was unemployed 2 months in Israel waiting for Microsoft to give me work permit, I thought this is a good time to be challenged. And so what is Kneser Ney smoothing? Kneser Ney smoothing is a language model which is used in speech recognition, handwriting recognition, in machine translation, and other applications. It's basically a model which is used for computing probabilities of n-grams, which is just basically probability of a word following other sequence of words. There is a lot of different algorithms. One of them is Kneser Ney, but there are other ones from Jelinek, Mercer, from Katz, Bell, Cleary, Witten, and so on. A very good comparison of different smoothing algorithms one can find in a paper of Goodman and Chen, an empirical study of smoothing techniques for language models. Besides that, this paper compares all these different smoothing algorithms, they also point out which one is the best, and they show some nice properties of Kneser Ney smoothing. Besides that, they show also some heuristic formulas for some parameters of the Kneser Ney smoothing, which enhance further this algorithm. And I will also make a small comparison between these two approaches. So what are smoothing algorithms and why are they used? So if you would compute probability of a word following another word, you would use counts of these couples, which you have in training data set. But because in your training data set, not every possible combination can appear, you would receive a lot of zero probabilities. And this would lead to very bad performance issues. And this is why you want to assign them some non-zero value. And that's why you are smoothing between two models, between bigrams and unigrams. So you are using also probabilities of these singletons, not only of these couples. So why small data sets? So imagine you are speaking with a child, and imagine you are speaking with your colleague. You use different vocabulary, you use different structure of words, and so all the probabilities of these singletons and also probabilities of these bigrams are going to be different. And so if you would have a huge data set which would consist of all different topics, speaking with a child, speaking with a colleague about something, you would just average the results, and it would also lead to bad performance. If you know the topic of the application for which you are going to use Kneser Ney smoothing, it's way better to use only training set containing this topic, and then you receive better results. So this is the reason why you want to use small data sets, but that also brings some other disadvantages, which I will speak about. So my challenge was simple. I had Kneser Ney smoothing. I wanted to improve it, and I didn't know how. So I took a nonlinear transformation, dy, with parameters alpha 1 and the rest parameter 0. In such case, you get equality. And no matter where you apply, on which term you apply this transformation, you will get just the same results. My goal was to try to improve it by using some gradient methods to improve parameters alpha and improve entropy and get some better results, hopefully. But I didn't know where I should apply this transformation, if it's going to work, and how it's going to work. So usually, you have training. You have data set which you split into training set and testing set. You train different algorithms, or you train different algorithms, and then you compare them on the testing set, their performance. You measure it by measuring entropy. But because I had also my parameters alpha, which I wanted to optimize somehow, I had to split into my data set into three sets. One was for training for the parameters, then for optimization of parameters alpha in my transformation, and then testing set was just to measure performance of different approaches. So as I was trying to apply my transformation on different terms of the formula, I realized often that I am getting better results of entropy on optimization set, but I am not getting better results on testing set. And so I realized this Kneser Ney smoothing is really good because it's hard to improve. But then one day, after applying it on the term for the unigrams, I got better results not only for the optimization set, but also for testing set. And so my question was, so in the paper I already mentioned from Goodman and Chen, they are also improving already Kneser Ney smoothing by having more parameters D, and they also have some heuristic formula for that. So my questions are these approaches different? Because they might improve the same thing, they just look a little bit different. And so questions are they different, and what is different? So I took a simple example. Imagine having just two words in your vocabulary, D1 and D2. The word D2 appears after word D1 frequently, and also word D1 appears after word D2 frequently. But let's say that there is also sometimes happening combination D1, D1, but this is happening very rarely. And with this example, I wanted to see if there is possible to fix with the transformation or with the parameters D, which Goodman and Chen are suggesting, if it is possible to fix such situation. So this rare appearance of D1, D1, imagine it will happen in your training set. So you would assign probability of D1 happening after D1 quite high because it appeared. It's very rare, but it appeared. And so the question was if you can actually fix that. I'm not going to go into details. If you want to see the details, you can check the paper. But what I realized was that with transformation T, you can, but with the parameters D, no matter what you do, you are trying to achieve 1/3. I'm not going into details, just giving you the results because it's very technical. So there is one value which you are trying to achieve, and that's 1/3 to get the optimal value, or to have ability to improve results further, to fix this rare occasion which happened. And with parameter D, no matter what you do, it's always very far away from this 1/3. So that was the first example in which I found out that these two approaches can be different. With the transformation T, I could improve this, fix this. With the parameters D, I couldn't. Another difference is when you look at the formula, is that parameter D is connecting all the couples. So it doesn't connect singletons, it connects couples, two words, such that these counts of the couples are same. What transformation T does is connect singletons such that counts of the singletons are same. So this is another huge difference between these two algorithms. The question is now, why does it work? So as I said, we want to use small data sets because those are bringing advantages if you know the topic of the application. And so why does this approach work on a small data set? So just imagine having two words again, and every single word appears with probability 50%. And just imagine you are doing simulation, and you are trying to get, for example, 9 words, and with every word appearing with this probability. But because it's a random process, you will not achieve exactly 50%, but you will achieve something very similar to it. And so you will have errors in your what you wanted and what you achieved. And as you are enlarging the data set, these errors are getting smaller and smaller. So on the left, it's a small data set. In the middle, a little bit larger. On the right, a little bit larger. And so on the right, you have smaller errors. And so the reason why it works is exactly this. You have a small data set, and so these unigram probabilities which you are trying to fix in the original Kneser Ney smoothing tend to be wrong. And this is the reason why it works. There is something what you need to fix. So as I ran the algorithms, I had a numerical problem with my transformation t. So if you look at the equation, the transformation t is used in numerator and also in denominator of the original equation of the applied terms, if you apply it. So if parameters alpha are solution, then if you multiply it by any non-zero coefficient, this is going also to be solution if there is one optimal solution. And so this coefficient will just cancel out. So as you are trying to get better entropy and you are using some gradient method, while you are improving the entropy, your parameters start to grow because there is so many solutions, optimal solutions. And you get into numerical instability. And so what I had to do was just to fix the first parameter alpha to 1 and the rest to optimize. And with this, I got rid of all the possible, all the solutions, and I got only one solution. And this is why the algorithm started to converge without troubles. So I had 5 different data sets on which I was trying my algorithm. And so on the upper graphs, you can see results for the transformation. On the lower graph, you can see results for the parameters d. Y-axis is improvement in % of entropy, and x-axis is degree of the polynomial of transformation t, or in the lower graphs, it's number of parameters d, which we are trying to fix. And as you can see, there are always 2 lines. One is dashed, and that one is improvement on the optimization set. And the other one is improvement on the testing set. So as you can see, as you are improving results on optimization set, you also are improving results on the testing set. But this is not seen for the parameters d. And this was the first result. But as I said, this is only one test for one data set. So, is it going to always behave this way? There are always these questions. And so I ran.
Can you go back to the?
Sure.
So what are the rest graphs here?
Which one?
What are the other graphs here?
So these are just 4 different data sets.
4 different data sets. I see.
Yes.
Okay.
And so they have different sizes, different counts. So yeah. And so what I did was I randomly redistributed all the sentences in the data set between these 3 between training set, testing set, and optimization set. And I ran the same simulation 1,000 times. And then I made average results to be sure that what I'm seeing is really going to happen. And then I again received the same results, saying I'm improving the results with the transformation on the optimization set, but also on the testing set. What I realized with the parameters d, while you are improving the results on the optimization set, you are not improving them on the testing set. But with 2 parameters d, you actually get some improvement, which is around 7%, 6%, and 5%. But then there was one data set, and with 2 parameters, you actually got improvement around 26% with 2 parameters d, and with polynomial of degree 9, with transformation, you get only 15%. So there was another question. What if you are going to combine them? This would really show if you can combine them and get some results even better than using them by themselves. That will be showing again that combining these 2 approaches is, so these 2 approaches are different in that case, they are improving different things if you can actually combine. And achieve even better results. So I tried to combine them, and if you remember, so there was 25% for the two parameters d, and now using the transformation t and also these two parameters, I could achieve around 40% improvement. And this is just another data set. So again, you start around 6%, which was introduced with the two parameters d1, d2, and then you also apply on it transformation t. So this showed that really these two approaches are fixing something different. On the right graph, you can see the difference between entropies, between the transformation, when you are using transformation t with two parameters d1 and d2, and standard Kneser Ney. So as you can see, if there are some cases which are on the right, it means the performance of new algorithms is worse. But as you can see, it happens very rarely, and almost all the time it's on the left from 0, meaning the improvement. And on the average, you get better results. And so I could find out how it feels when you do things people say you cannot do. Thank you for your attention. If you have some questions, I'll be glad to answer. And if you want to see details of the paper, you can check the paper in IEEE Transactions on Audio, Speech, and Language Processing.
So I have a question. So those small data sets, like you assume that the words are random, but in reality they're grammas, right? So that actually skews the probability of words appearing in sequences. Is it correct? You don't consider any grammas in those data sets.
Because there are grammars, the probabilities are not completely distributed, and there is some structure actually in that.
Right.
But so we are training on some data set which contains not the random words. It's just you train on something real, some real sentences.
Okay.
You don't create this training set randomly by distributing words. For example, sorry?
You discover grammar statistically by
Yes.
data sets.
Yes.
So what are the nature of those data sets you are using?
So one of them is a book. One of them is articles in newspapers from the same web server.
How big are they?
So the sizes. So it's from 29 kilobytes to 72 kilobytes. It's a plain text file. And you can see counts of, so this is number of words. I don't actually remember. Number of words and number of, yeah, yes. So those are still pretty small data sets. But as I said, yes, go ahead. Go ahead.
I was just wondering, so the whole thing is framed in terms of small data sets. Are we to
Yes.
assume implicitly that you tried it on large data sets and it doesn't help?
So yes. And why does it work on large data sets is explained here. So you're trying to fix the unigram probabilities, and as you enlarge your training set, just there is nothing to fix anymore. So that's a simple reason.
So can you go back to the previous slide? That's it. Yeah.
This one?
Yeah, this one. I didn't quite get what you are trying to say with the right.
The right graph?
Right.
So I didn't really explain it. I just gave you the results. So there is the part of the formula which has to be, I don't remember which one exactly, but there has to be one part of the formula which has to be 1/3 to get optimal results. And with this graph, I just wanted to show that no matter how you set parameter d, So if you set d from 0 to 1, it's somewhere in
It's
here.
a term in Kneser Ney.
Yes, so this parameter d.
I see.
So no matter what you set, how you set the parameter d, you get this value far away from the 1/3. So no matter what you do, you have no chance correcting these mistakes. That's all I wanted to say. And yeah, I didn't want to go into details because it's very technical. You just grab this example and you just try to fix something, and you realize at the end, oh, I cannot fix this parameter d.
I see. So you have to use transformation to fix that.
Yes, and with the transformation which I'm suggesting, but I'm fixing exactly this, like singletons, not the couples. You can do that. So those are the differences between these two approaches.
More question?
So is there any, your conclusion, does that, is that in agreement with the previous, evaluations with the, same smoothing, or some, I clearly, missed something.
Can you go back to the results slide to show again what's, yeah.
So basically this is the main result. And so you have the results for the transformation, and you have the results what Goodman and Chen suggested for parameters d. And so the dashed line is how you are, so you have some parameters which you are trying to optimize. I will just go back just to repeat this. So you have a training set on which you are which you are training the parameters. Then you have optimization set, so you have some additional parameters which you are trying to fix, and then you have the testing set which you are measuring the performance of these algorithms. And so the dashed line is the results on the optimization set, and then the full line is the result, so that's the testing set. And so for the transformation t, while you are improving the results on the optimization set, you are also improving results on the testing set. And so this is the entropy, improvement in entropy in percent, and this is the degree of the polynomial t, which you are using. And so Goodman and Chen, they suggested to fix the parameters d. And what I realized is that with two parameters d, you actually get better results, around 7%, 7%, 5%. But with more parameters d, it doesn't fix anything, because while you are improving the results on the optimization set, the results on the testing sets are actually going down. So
what is the why it goes down?
Well, the reason why it goes down, and the reason why I think it goes down is exactly this difference between these two algorithms. So you have a small data set, and so if you have a small data set, these parameters d, they are combining the couples. And so because you have a small data set, there is a lot of couples which have 0 appearance, which have 1 appearance, and perhaps few of them a little bit higher. And so it's like you cannot really segment anything. If you are trying to fix singletons, you have appearance of words which appear like 20 times, 50 times, so you can segment things more. And this is probably the reason why it works with that and why it doesn't work with that.
So have you any speech recognition result on this smart data?
I didn't do anything like that, so I don't know how much it actually improves. So, but I think I read somewhere on the internet that the small improvement of 6.
To the result, I want to see the entropy. How much is exactly is the entropy difference?
Oh, okay, where is it? Okay. So entropy is here difference.
Let me see.
I read somewhere that around 10% of entropy improvement is like 1% in speech recognition in the final.
He was saying the square root. Right?
Something like that. I read somewhere. One paper, but I don't know how good this paper was. So I also was interested to know how much actually are going to improve it. But yeah. So if you know, you can tell me.
It all depends on tests, right?
Right.
Yeah, but it's definitely very small. It's definitely very smaller than actually improvement on the entropy. So I didn't have chance to test that. So
How do you think your transformation will scale up with a larger scale program?
like with the large data set,
Yeah.
it's not going to work.
Okay. Yeah, as you showed, so in a larger case, you may not have anything to fix.
Yeah, there is nothing to fix because this estimate is going to be correct. Okay. But there is a reason why you want to use small data sets, and the reason is different topics. So, and then you can get, you don't average the results of different topics of these estimates, but you actually use only the topic, and so there are good reasons to use small data sets.
Yes.
Okay, thank you.
Thank you.